Welcome back, chat. Today we are continuing on. We were looking at 4.2 last week, and I just want to kind of touch base and make sure that we can see and agree that this is all the stuff we talked about. Weight, always, always, always in newtons. We're not going to give weights in pounds or kilograms, those are masses. Weight is literally the force of gravity, Fg, that we can find by taking mass times the acceleration due to gravity. Oftentimes, though, notice it is more convenient instead of saying ma sub g, we just call it g, where g will let be this 9.8 newtons per kilogram. It is the exact same thing as a meter per second squared. The label just makes it so it's a little bit easier to pick out and play the unit game to get down to newtons. Okay, with that, we did this problem the other day, which is a tricky one. I will not give you guys the super tricky ones necessarily, but I mean they're fair game. And then we had the assignment. Then with the last couple minutes of class, I believe that we just went in and we started apparent weight stuff. So we'll slide that over. Hate it. Sorry. Slide this over so it fits nicely. And then we'll just get to it. Cool. All right. So zooming in. There it is. Boom. We talked about apparent weight the other day. And remember that oftentimes we have these situations where if you're moving up or down or whatever the case is, you may feel as though you weigh differently because within your relative position, different forces are applying. However, in reality, your weight isn't truly changing, it's just perspective, right? Your mass obviously doesn't change, your volume doesn't change, it is just the forces that you're feeling. So if an elevator moves up, you feel heavier because the scale exerts force upward onto you, and in turn, you exert a larger downward force onto the scale. The opposite is true if the elevator is moving downward and it starts accelerating down. The scale is moving away from you, so now you are pushing less on the scale, which means you're lighter according to the weight. Now, if the cable snaps, everybody's free falling, and all of a sudden there's a huge issue. If you are in free fall, like this is talking about, the elevator is snapped, the cable snapped, what's it feel like as you fall? Let's say you're in like an unbelievably tall building and you just start falling. What's it going to feel like from your perspective? Like there's no weight, just like the gravity in space is truly there, but when you fall in space, it's called orbit if you fall with the right angle, and you just feel weightless. Okay, so did we write weightlessness last week or no? This is the last thing you guys have written? Okay, so continuing on then, we get a couple of problems that we're going to look at. However, we are first going to pick this lovely purple color, and we're going to define this for ourselves real quick. If your apparent weight equals 0 newtons, then you experience what is known as weightlessness. And I hate that they make this a vocab. And I'll count it as a vocab, but I don't know it's going to show up a ton. Weightlessness. Holy consonants. Okay. There is nowhere in the universe that you have no gravity. Like just nowhere that exists. Like we always use that language. You may have heard or even heard somebody say that gravity on, like as we orbit, there's no gravity. That's not true. It can't be true. There is gravity every single place in this universe. As long as there's two things that exist, there's always a gravitational attraction between them. We'll go more into that later. Gravity always exists. What may not always exist, though, is this sensation of weight, which is if you don't have anything to push against, then you don't feel any weight. Cool. We are going to do a problem together, and I wish that I had printed these out, but let's knock this out. Okay, so you guys don't even have the problem here. I am going to type it out, and I'm going to try to make it as not wordy as possible, so terribly sorry about this. So thanks to the little editing magic. If you need to take a second to pause this and write that down, please do so. We have Erica on an elevator. It's going downward at 2.5 meters per second squared, or it's accelerating downward. We know that they have a combined mass, and we are looking for the force that holds up the elevator. Okay, Now, as we deal with this, it is always a good idea, not required yet, but we should probably start with this thing that I'm going to call FBD. What is an FBD? A free body diagram. Now, it doesn't have to be like an awesome picture or anything like that, but we should make sure that we at least all agree on what this problem is saying and how it's set up. Okay, right off the bat, I'm not going to draw Erica standing on an elevator. That's absurd. I mean, I am, but it's not going to be a picture of her on an elevator. Here they are. Look at them. Elevator and Erica right there. Now, at this point in time, it's moving downward. We'll deal with that here in a second. What forces are acting on it? What's pulling the elevator downward? Gravity. So here's a vector going away from this. I'm just going to say, check it out. That's a force of gravity. Now, luckily, there's more forces than just this acting on it, because otherwise you would just be falling to your injury. What holds the elevator up? It's a cable, and specifically the force that we've named in this problem, the force in that cable that holds it up is known as what? Tension. So there's tension in this cable, and I want you to tell me what's wrong if I do this. Don't write this down yet. What's wrong with this picture? They're the same, which would imply that she would be standing still, right? She's accelerating which direction? So there better be more downward force than there is upward force. And I'm not going to draw it like super to scale, but I assume that maybe something like that. Here's our force of tension. Now, I know the acceleration is downward. If you want to indicate this off to the side, oftentimes I'll make sure that it's really clear. And I'll just have a small vector here that'll say, check it out, there's my acceleration. Okay, we have a good idea of what's happening now. We know that gravity better be larger than tension. Okay. Well, in problems like this, we have our nice free body diagram given. We have some known information. We should probably record what it is we're supposed to find, and then the equation and all the work that goes into this. Now, these problems can get kind of challenging to start thinking out, so let's just check everything that we possibly can with it. I know 3 known things for sure, maybe more. 2 known things for sure, maybe more, I guess, there. Can you give me one of the knowns, Nick? We made eye contact there. The mass. So they're mass together. I'm not even going to bother, weird, writing combined or anything. What is the mass of the object or the system that we're looking at? 1,250 kilograms. Cool. Is there anything else that we know? We know acceleration. And let's say acceleration is what? Negative 2.5? Meters per second squared. And I think there's one more thing that we do know. I know the acceleration due to gravity, or the force of the gravitational field, which I'm going to represent with G. And what is G in this problem? Any problem, really. We're on Earth. Negative 9.8. And then as soon as we decide to call this G, what should my unit be here? Newtons per kilogram. And remember, that's the same as meters per second squared. It's just we have simplified to make it look a little nicer. Okay, what are we trying to find? The force of the tension, right? So here's our goal. Okay, looking back, and we're going to make sure that we can get some nice stuff organized and set up for us. But we have talked about force in a few different ways. We know that if there's a bunch of different forces acting on an object, they're not going to balance out, right? Unbalanced forces are what cause movement. And I know for a fact that we have an unbalanced force here. Do you remember what we call it when we add up all the forces that are acting on a system? Check your notes for me rather than me just giving to you. F sub something very specific. Net. Okay. When we're looking at this, we're going to have more equation stuff than we probably have on any problem up to this point, but that's okay. if I wanted to start in trying to find the force of tension, I'm going to relate it to this idea of net force that we've dealt with already. So to do so, let's make sense of this. I know that F net, or the net force acting on this object, is just the sum of all the forces. What are those forces that are acting on this guy? Say it again. So not careful, mass isn't a force. Let's look at our free body diagram, and I can already see them. What are the only two forces acting on this? Gravity and tension. So do you guys agree that the overall force could be looked at as being the force of tension plus the force of gravity? Everybody okay with that idea so far? Now, going in here, there's a few different ways that we can knock all of this out. If you wanted to find the net force, do we know the overall mass? We know the mass of it, right? Do we know the acceleration of the whole system? So check this out. Can we do, without plugging in numbers yet, and I need really honest feedback between you guys, on this left side, the net force is just going to be mass times acceleration. Everybody on board with that still? Okay, this is still equal to the force of tension we're trying to work out, plus, do we know how to calculate the force of gravity? Say it again. So that's the acceleration due to gravity. How about the force? How do you find any force so far that we've seen? It's mass times something. Acceleration, but if it's the force of gravity, then it's mass times g, the gravitational field, which is also can be looked at as acceleration. As we do this, I just want to look, do you guys agree with the little substitutions that we've made so far? And can you tell how I've elected to write these? Now, I'm not plugging in numbers yet because there's a lot of numbers and the units get ugly. What are we trying to solve for? I'm trying to solve for f of t, or f sub t, I'm sorry. To isolate just this, and I'll make a little comment here, substitute is all we've done. We just substituted in known stuff. Now, I know the mass is going to be the same for the force of tension that we're dealing with, but I'm going to hold off a second, because if we can just solve it for f sub t, or the force of tension, then maybe we don't even have to worry about plugging that in. If I wanted this to say only f of t, oh my goodness, f sub t, the force of tension equals something. Can you rearrange this equation so that it's only the force of tension on one side? It'd be mass times acceleration, which we have those very clearly written. And what do I need to subtract from this? mg. Is that what you guys just said? I just heard murmurs. Okay, and I'm just going to say subtract. At this point, when I did this problem, I didn't have a calculator handy as I was looking at it. I would factor. Just a little tiny bit to make this easier, only because I didn't have a calculator. What goes into both of these? So, in its most simple, this is just mass times acceleration minus gravity. Again, I've only factored this out because when I did it, I didn't have a calculator, but I do think it makes it look a little bit nicer, less writing. Once we get here, let's just check. I have the force of tension equal to this stuff over here. Let's just see if we can work it out. What is the mass that we're dealing with? $1250. So here we go, 1250. And that's in, I'm going to play the unit game underneath. There's kilograms. What's acceleration? Say it again. Negative 2.5. Minus, and this is where it's going to get weird for just a second, that's meters per second squared. Minus, what's the force of gravity, or g? Minus a negative 9.8. And I can go ahead and we can write newtons per kilogram, or if you'd rather, and maybe it makes it look a little bit nicer here, kilogram meters per second squared. Would you rather I write newtons per kilogram? especially those of you that weren't here the other day, do you know why I'm like, can you tell why I'm allowed to do this or no? So we did this in our notes the other day. You do not have to do this again if it's white, everybody. I just want to review this really quick, and then I'm going to see if you can tell me why I've done this. A Newton per kilogram, let's just see what this shakes out as. Newtons are kilogram meters per second squared over kilograms. These wind up falling out, and we get the exact same thing. Now, instead of writing newtons per kilogram here, I have very specifically elected to do this. Can anybody tell me why? It's just newtons, so careful. This is still newtons per kilogram. It is. It's newtons per kilogram over. So I just simplified using that I've already raised. I have elected to do this specifically because we see newtons per kilogram should be meters per second squared, right? Yeah, we're okay. I look at this and I see my units are going to shake out. Okay, here. Now, the only part that I'm concerned about anybody making a mistake on is going to happen right here. What happens right here? It adds. Okay, so when we look at this, grab your calculators for me, and I just want to be able to find this answer. The force of tension on this cable, whatever 1250 times that is, and I'll take one more little step here. That's 1250 times 9.8 minus 2.5, must be 7.3. And whenever somebody gets an answer, don't hesitate to keep it to yourself. Shout it out. And Fern, you were right. That should just be meters per second squared, right? Yep, that's my bad. Do we get 9100? Is it exact? Okay, I'm going to call it 9100, just with rounding. And then check it out. If we look at our units, and I did change that because my kilograms were gone, my bad. When I change this, I have kilogram times meters per second squared. Kilogram meters per second squared, what's that unit? Newtons, which is how force should be measured, right? Now, once we get all of this, I really want to make sure that we always, always, always make it a habit of this, and I'm going to start doing it more in class than I have. As we deal with this, what should my final answer say then? Like, how would you write your final answer? The tension pulls up or down? Upward with how many newtons? 9100 newtons. Now, that is a huge amount of force, but it makes sense because elevators are super heavy and these things are moving. There's a reason that they're made of metal and strong. They're steel wires is what they are. Okay, this problem. Feel okay? Feel awful? Should we do one more together? Together? Do you guys want to try one on your own? Okay. So, let's check it out. This problem's not very exciting, but that's okay. Uno mas. So, this is a pretty hardcore problem, at least compared to the other ones. I want to really specify that this here is going to wind up being super duper helpful as we move forward. The net force, that idea is going to keep showing up. One more really quick problem that I want you guys to do. Let's see. Someone's weight, a person's weight is 585 newtons on Earth. Okay, I have two things I want you to do. I want you to, on A, find their mass. And then on B, I want you to find their moon scale reading. So weight on moon. Weight on moon if the gravitational field strength on the moon, which you can just write G if you want, but I'm going to be really specific. I'm going to tell you that this is equal to negative 1.6 newtons per kilogram. Very similar problem. All the same ideas are here. Bit simpler. But I'm going to give you guys a second. Find me this person's weight, or their mass on Earth, and the moon rather, as well, apparently. And then find me their weight on the moon. I'm going to give you guys a second. I'm going to pause it. When you resume this video, you will see a detailed solution. But I'm going to give you guys a head start. Now, looking at it, part 1, we got their mass. All of a sudden, then on B, once we know their mass, can we find their force of gravity or their weight on the moon? I think so. What's that equation? Force of gravity is equal to the mass m times, in this case, it's g moon. And I think we have these numbers. It is just going to be 60 kilograms times 1.6 newtons per kilogram. And what do we get for their weight on the moon? 96 newtons. Okay, and I should make this more of a point. On the moon, they weigh 96 newtons. Does this problem feel easier than the tension problem that we did a second ago? Okay, in reality, they're essentially the same problem. We just had one more force to deal with because we weren't just standing on the ground. Going through here, this stuff feels okay, feels awful. Good. All right, so I'm going to take like a 30-second or a minute long, we'll see if it winds up longer. I'm going to do a quick brain break because I want to show you guys something cool. We get to discuss a little bit more. All right. I hate that this just doesn't work the way I want it to. Cool. So we are halfway through this section. We get to start our second main topic today. This overall section, 4.2, was called weight. We've knocked out weight. It's a force of gravity. Easy. What else were we talking about, though? Do you guys recall? Drag force. So we are going to sneak in right off the bat. Continuing on, we're going to define for ourselves the idea of drag force. All right. More talking than writing is always my goal. Hopefully it comes out that way. More talking from you guys than me is also an aspirational goal of mine. All right. What's a fluid is a question that I have right now. When I say fluid, what do you think of and how many different fluids can you name? I'll give you a moment. Talk with your neighbors. What's a fluid? All right, so I have a pretty good feeling. Who says liquid? Like you probably went water, coffee, soda, whatever. Like you probably listed a bunch of them if you had it. You're not wrong. Liquids are a version of fluid. If I said right now I'm walking through fluid, does it feel natural to you? Probably not, because when you think of fluid, you think of fluid ounces. This is where my head goes. You think of like a bottle that has fluid ounces specified. Okay, liquids can be fluids. However, this is fluid. Anything that we pass through that's not a vacuum, whether it be air or water or something thicker than water or thinner than air, it doesn't matter. When we're talking about fluids, it's just the medium that surrounds us. So in space, there is no fluid because there's no gas, there's no liquid that you're traveling through. It's just a vacuum. When we're talking about drag force, it is required that we are working within a fluid. So by definition, we're going to assume that we're working in our fluid, and our fluid right now is just the air in this classroom. Drag force, we're going to say that by definition, it is the force. It is the force exerted by a fluid, which, remember, this could be air, liquid, jello, whatever you want. The force exerted by a fluid on an object that opposes motion through the fluid. Opposes motion through the fluid. All right. Now, it turns out that there are a ton of factors that are going to determine your drag force. If I asked you guys to sprint as fast as you can, and you tried it just regular, and then I hooked a parachute to the back of you, it's harder to run, right? Now, this is a weird question. Is it easier or harder to swim through air, which is a weird idea, or water? Way harder. So maybe it depends. I heard somebody say air. Maybe it's hard because you can't really swim in air, right? Because we're not suspended in it. Swimming is hard because as you try to push through the water, what does the water do to you? It pushes back, right? So like there's a whole variety of things that people do to reduce the amount of drag that they're experiencing. Whether it be swim caps or aerodynamics with vehicles, like these things are always accounted for. Now, as we're looking at this, the drag force, I'm just going to specify, I know that we talked about this. For our purposes, we will let fluid, we'll just say is liquid or air. Now, liquids and airs, they vary wildly. Have you guys ever seen those little toys? It's like a sphere that has a little fan in it, and they showed up on my Facebook, and they're super fun to play with, but you push the button and then you toss it up and it like drifts because it's like a fan that blows down. Okay, I bought one when we lived in Wyoming. Didn't work. Like, it sucked. You would just toss it and like fall a little bit slower, and I thought, well, that's kind of lame. Then when we moved back here, it worked really, really, really well. And all of a sudden this thing would like float around the room and you could toss it and it would just go and go and go. Eventually it would come down, but it'd be really slow. Both were air, both were fluids. Why did it work here but not in Wyoming, do you think? What about it? So, what about the higher elevation? So there's less air and less dense air. A denser fluid exists here than it does at, a mile high, which is where I lived before. So just those little changes, huge impact. Beyond that, we always experience drag forces. Even right now, I don't really feel it, right? Like I'm walking through the air and obviously I have to push the air out of the way and it pushes on me. Right now, can you guys feel all the air pushing on you? No, but is it? Now, even as you're like barely moving, there's air pushing on you. It's known as air pressure. An easy misconception about this though is that we think of like the pressure that we feel is a result of all the air above us, right? Now, particles are always moving inside of stuff. You guys remember talking about the particle theory of matter with probably Ms. Holloway? All right, so we're going to hit it really quick. Everything is made of little tiny particles. You guys go with that? Like you might call them atoms or molecules, whatever, doesn't matter. All those little particles are moving. Now, they're not, depending on the situation, they might be moving just a little tiny bit or they might be going crazy. I like to think of them as buzzing. They're just buzzing constantly. Okay, as we deal with pressure, if we think about them buzzing, there's pressure pushing down on me from the atmosphere above, which makes you think that maybe it only pushes down. However, is there air right next to me that's still buzzing and moving around? And it's moving with the same amount of energy because all the weight above it is pushing to my sides as well. As I hold my hand out here, air pressure pushes down. Does air pressure push up as well? Absolutely, because all these little particles that are hitting right here, they're also doing it right here, and they're doing it right here. Everywhere I'm being pushed on. We don't feel this drag through the air just at regular speeds, but it does happen. It just happens to be the same from every direction. Okay, in water, it's much more clear. When you go down 10 feet, 5 feet in the water, what do you have to do with your ears? Why? The pressure in your ears, right? You have all this water above you. Does it matter if you go with your head up or head down or sideways? Like no matter what orientation you are, you feel the water pressure pushing on your ears. It comes from all directions. I want to make sure that that's kept in our minds. So, drag force happens when we try to push through a fluid. Anybody in here willing to jump out of a plane? Just that? Just right out of a plane. You might be if you have what? A parachute. Why? What is that parachute going to do for you? It's going, well, kind of. It's going to make you fall slower because it's going to increase your what? Your drag force. Now, we have one problem that I want us to play around with, and then this will be the last thing that we are going to do today. So here we go. Quick example dealing with our first kind of implementation of drag force. We have a 415 kilogram supply crate. That is dropped from a helicopter at 300 meters. Dropped from, can I just say heli? Good. At 300 meters. All right. Welcome to Call of Duty. As we go through here, I have 2 questions that I want you guys to deal with, and I'm going to give you the next 5 or so minutes to try to knock this out. I want you to do it in your notes. But part A, I want to know how long to strike the ground and how fast will it hit. And I'm going to say maybe differently than I write. If I say in a vacuum, what does that mean? Louder? There's no air resistance. I'll just say here, no air. Which means there's no drag. If there's no air, there's no fluid for you to move through. Okay, I want you to do the nice version of this with no air. Once you get that value, I want you to try B. Let's say that in reality, so truly, the drag force produces a constant velocity of 6 meters per second. I want you guys, with that little piece of knowledge, I want you to find me the strength of the drag force. What is F drag? Cool. I'm going to give you guys to the end of class. I want you to do this problem in a vacuum and then see if you can expand out the constant velocity once it falls, because the parachute has to open, and then it falls at 6 meters per second. I want you to see if you can find the drag force, which is kind of like the tension on the previous elevator problem. Just a different cause for the upward force. Okay, I want you guys to try this, talk it out. We will look at the solutions to these tomorrow. Rest of the time is yours. There is no additional homework other than I want you guys to try these problems. Cool.